Hi, my name is Xia. I would like to introduce our work FG2 fine-grained cross-view localization by fine-grained feature matching. In dense urban areas, specialized localization sensors such as GNSS can exhibit positioning errors of up to tens of meters. For autonomous driving and outdoor mobile robotics, mapping an entire city using SLAM is costly. In such scenarios, cross-view localization offers a promising alternative for localization. The task of fine-grained cross-view localization is to estimate the 3 degrees of freedom pose, or namely the planar location and yaw orientation of a ground-level image on an aerial image that covers the local surrounding. Previous fine-grained cross-view localization method typically maps the ground view to a bird's-eye view representation, for example using homography. Then they estimate the pose by setting window search or use a model to regress the pose from the dense feature matching. However, homography applies only to flat ground planes, and the matchable information between ground and aerial view is sparse. If we think about how humans would perform this cross-view localization task, they often match distinctive landmarks. For example, the top of a building can be matched to the roof in the aerial view. They can also match the road markings across views. In fact, literature shows that humans tend to localize based on a few distinct objects instead of the full panoramic view. However, existing datasets do not have such ground truth local feature correspondences for training. We propose to learn the local feature matching through the weak supervision on the camera pose. Here is an overview of our method. Our method starts from the standard feature extraction. Since our goal is to estimate the 3 degrees of freedom pose, we wish to conduct matching in the bird's-eye view space. As the aerial image is already in bird's-eye view, let's focus on the ground view. We first define a grid of bird's-eye view points. For each point, we lift it to a pillar of 3D points, spanning a given height range. Next, we can look up for each 3D point its feature in the ground image, following the projection geometry. Here we use deformable tension to allow the model to look around at the projected location. Once we have the feature for those 3D points, we let the model to learn to select the feature along height to pull the 3D points to bird's-eye view. Once we have the bird's-eye view feature for the ground view, we conduct matching between it and the aerial bird's-eye view points. Since the matchable information between ground and aerial view is sparse, we sample only a set of sparse correspondences for pose estimation using Procrustes alignment. Finally, we put supervision on both pose and the induced correspondences. Our method sets a new state of art on common cross-view localization benchmarks. Here we also show the qualitative results of our local feature matching. Because we explicitly classify feature along height, we can trace back in the image plane which feature contributes to the matching at bird's-eye view. Without explicit supervision, our method learns semantically consistent matches. For example, the points on the building facades in the ground view are matched to the roof in the aerial view. Here we also show the selected height when pulling the 3D points to bird's-eye view. The center vertical line in the ground image corresponds to the up direction in the bird's-eye view grid. For the area correspond to the buildings, our method learns to attend to higher points. We highlight that the model learns its selection from the camera pose, and we do not supervise which point to choose. Please find more details and results in our paper. Thank you for your attention.